triggering devices and firing circuits. In this chapter, we will be studying some of the techniques to trigger a thyristor. The first device is UJT, namely unijunction transistor. This is called an unijunction transistor because this literally has only one p-n junction. It has a diode-like structure, but the N region is larger and lightly doped. So this can be modeled by a p-n junction and some resistance. And as the resistance arises from the fact that this section is lightly doped, the resistance is variable and depends on the amount of carrier. When the device is on, the carrier rushes in and the resistance becomes lower. So if we name it RB1, it varies inversely with emitter current. So to turn it on, we must apply a voltage in this emitter region. By the way, this device has three terminals: base 1, base 2, and emitter. So if we apply a voltage in this emitter junction with respect to this base 1, the device will turn on, and the voltage should be the voltage drop in this PN junction plus the voltage drop in this resistance. So if we derive something that voltage should be equal VPN plus V into RB1, and again this VRB1 can be characterized by this voltage divider equation. If we apply a voltage VBB and the breakdown is RB2 and RB1, the voltage drop in this RB1 will be VBB into this portion. So this portion is called eta, which is the intrinsic standoff ratio. So this is our general equation of turning on the device. So during off state, there is a lower carrier concentration in this N region, hence a higher value of RB1. So a high voltage is required to turn on during the off state, which is known as VP. On the opposite side, during the on state, due to this higher concentration of carrier, the resistance RB1 is lower. Hence, a lower voltage is required to turn off the UJT. This is VV. So to simplify the theory, when the value of this emitter voltage exceeds Vp, the device will turn on, and when the value reaches below Vv, the device turns off. In case of a normal diode, this turn on and turn off voltage is same. But in case of an UJT, as there is some variable resistance and this resistance varies with the carrier concentration of this N region, we will get two voltages, one for turning on and one for turning off. The turn on voltage is called peak voltage or VP, and the turn off voltage is called VV or valley voltage. So if the device starts to turn on, the current will start flowing through this resistance, and as the current increases, the resistance decreases. So more current will start to flow, and as this is a positive feedback loop, the current will rise very fast. So this UJT can produce a fast current pulse, and as this internal resistance decreases with the current flow, we will get a negative resistance region in this active region of UJT characteristic curve. The negative resistance region means the value of current increases with a decrease in voltage. Normally, in case of a positive resistance or positive slope of resistance, the voltage and current is linearly proportional. If current increases, so does the voltage. But in case of an UJT, due to this negative resistance feature, the current will increase with a decrease in voltage. So when discussing the applications of UJT, we have to keep something in our mind. The UJT turns on at Vp, it turns off at Vv, and it produces a fast current pulse. So if we connect the UJT with an RC circuit, as the capacitor is connected to the emitter terminal of UJT, when the voltage is below Vp, the UJT doesn't turn on. So the capacitor will get charged through this resistance, and the charging curve will be something like this. When the voltage of the capacitor reaches Vp, the UJT turns on and the capacitor starts discharging through this resistance RB1. So if we measure the voltage of RB1, we will only get the voltage when the UJT is on. So we can trigger the SCR by this voltage in this base one, and we can control the triggering time by this delay or this charging of the capacitor. The charging of the capacitor is this simple KVL equation. The voltage in the capacitor is the voltage of the source voltage minus the voltage drop in this resistance. So the voltage drop in this resistance can be characterized by this exponential charging curve. So if we put this value in this KVL equation, we have something like this. We have derived this portion of the equation previously. This is basically this equation. So if we ignore the voltage drop in the diode, we can reduce the equation to something like this. So if we get back to our main slide, we can get the charging time of the capacitor from this equation. So if this resistance, the capacitance, and the value of this eta is provided, we can determine the charging time or delay time of the trigger by this equation. So here is a quick math that uses this formula to calculate the value of R3. This T is derived from this frequency. T is equal 1 by F. So if we want to construct the firing circuit, we can follow the circuit we've used in our laboratory experiment. This is the firing circuit. This is the UJT. This is the RC network. And this is the isolation circuit. And this is the main circuit. So if we connect this point to this point, we will have a half-wave rectified output like this, and the charging and discharging and the trigger voltages will be like this. Here is a correction. This shape of discharging curve will be similar to this one, and this charging curve will be exponential. So in these types of circuits, a synchronization is required. For example, if I trigger this main circuit in this second half cycle, nothing would happen, because we need to trigger the main circuit in the first half cycle and the third half cycle. If we trigger it in the second half cycle, the output will be 0. So a synchronization is required. So in this circuit, this synchronization is done simply by using this diode. Due to this diode, the entire triggering circuit will be turned off during the second half cycle, and it will be synchronized in the first and third half cycle accordingly. So in case of a practical circuit diagram, you can follow this laboratory circuit diagram. Now the programmable UJT, which is very much similar to the original UJT, except for the fact that this triggering voltage can be changed. In case of an UJT, we have to trigger the UJT using VP and VV. These are fixed value. But in case of a PUT or programmable UJT, we can alter this value. Here is the basic construction of a PUT, and it is very obvious that in order to turn the device, we need to forward this PN junction. So the anode voltage and gate voltage must be set apart by this, the voltage drop of a diode. So VA minus VG must be greater than 0.7 in order to turn this PUT. So we can adjust this value by this voltage divider network R2 and R3. Other than that, the characteristic curve is similar to that of an UJT. So this is a practical circuit diagram of a PUT. Different values of resistances are connected to this circuit, and this formula is basically the same we have derived earlier in case of an UJT. This formula is this. So we can calculate the charging time of a triggering circuit using PUT. Again, this is the value of eta. So if we know the values of resistance and capacitance, we can get the value of this timing or the frequency. This is a very easy math. DIAC. DIAC is the acronym for diode alternating current. This is a basic construction. You can imagine if an AC voltage is applied between the two terminals of a DIAC, one of the junction will be forwarded and one will be reversed. If the value of the AC voltage is high enough, this reverse junction will be subjected to a breakdown. And this type of DIACs are designed to operate in the breakdown region. They can eliminate the heat generated from this breakdown. Hence, there will be no device destruction. The characteristic curve of DIAC is similar to that of a TRIAC, but in case of a DIAC, there is no input terminal or no control terminal, so the DIAC can only be turned on by this breakover voltage. So once this breakover voltage is achieved, the DIAC is on. Here is an example of a DIAC circuit which is coupled with this TRIAC circuit. So basically in this circuit, the DIAC is used as a triggering device for this TRIAC. This very circuit is used in a ceiling fan regulator in our home. Note that the DIAC is connected to this RC network. So in case of an RC network, the input voltage and the capacitor voltage will be separated by this theta. So the capacitor voltage will lag behind the input voltage by this angle. This is the capacitor voltage and DIAC current. When a certain amount of capacitor voltage is achieved, the DIAC turns on and continues the cycle. The same goes for the negative half cycle. So you can clearly see that this is the delay angle of the trigger. Again, this delay angle is further increased by the amount of resistance. So the theta will also increase, and this delay angle will also increase with the increase in capacitance or the decrease in resistance. So in this circuit, we can change the delay angle or the triggering angle by changing the value of resistance, and the TRIAC will be triggered accordingly. Note that the DIAC is producing both positive and negative trigger, and a TRIAC can be operated with a positive trigger for quadrant 1 and a negative trigger for quadrant 3. Isolation. The first point of isolation is to isolate the high voltage and low voltage side. Typically, the control circuit consists of low voltage components, usually has a range of 5 to 30 volt, but the output circuit might have a range of more than 100 volts. So in these cases, we need to isolate the lower side or low voltage with the high voltage side. So you can see this in this diagram. So this terminal is supposed to be connected to the mains, these two terminals. So again, in order to trigger a thyristor, we need to provide a gate pulse with respect to cathode. So if we get to the two transistor model, you can see this. We have to trigger the SCR or give the gate pulse in the gate terminal, but the reference should be with the cathode. So in this case, if we avoid this isolation circuit, we must connect this terminal directly with this terminal, but this terminal is connected to the mains. So if someone touches this portion of the output, he or she might get a shock depending on the polarity of this mains. So this in this circuit where the mains are connected and the final output is a DC output, this two portion must be isolated. So an isolation circuit can be constructed by different ways. One of them is using optical coupling. This can be illustrated in this simple diagram. So this is the input circuit and this is the output circuit. It is clearly shown that these inputs and outputs are nowhere connected. So in this input circuit, we are providing a light signal, and this phototransistor is acting like a receiver, and the output of the phototransistor is fed to the main circuit. So these terminals and these terminals are these input and output terminals. So these are completely isolated. Just the information or the duration and the delay of the pulse is transmitted by this LED. An infrared LED is used in these cases. So this is optical isolation. Another kind of isolation is galvanic isolation, which uses transformers. So this is uh, a practical example of using pulse transformer. But if we only concentrate on this transformer, we can clearly see that the input side and output side of the transformer is electrically isolated but magnetically connected. So these types of transformers can be used to isolate the input from output. In this case, the input is the triggering circuit and the output is connected to the main high voltage circuit. So these are some other examples, and there is some descriptions. You can follow this. This ends our lecture on triggering devices and firing circuits.